So let's talk about this required practical to do with waves. Right, first things first, I should point out that this is actually a practical on two halves. You need to look at waves in liquids and also in solids. The liquid experiment will involve a ripple tank, and the one in solids will require something. Probably you'll do it with string. Okay, so let's get into it then. But before we talk about the actual methodology, let's talk about the maths. So you'll be using this equation quite a lot, the wave speed equation. Wave speed equals frequency multiplied by wavelength. So wave speed does exactly what it says on the tin. It's the speed of the wave, it's the speed that it travels at, and that's measured in meters per second. The frequency is waves passing a point per second, and that gets measured in hertz. And wavelength gets measured in meters, and that is the length of one wave. Okay, that being said, let's dive into the equipment and see about how you go about using this. So here is a diagram which I have done. It's kind of beautiful, really. So let me talk you through what is in my amazing diagram. This pink box here, this is a vibration generator, and it is basically going to vibrate the string. This over here are some masses, and they are going to hold the string straight, nice and tight. So this here is your string, and this over here is a pulley, just for your string to go over the top of, and this here is a wooden bridge. Okay, so what happens then is you switch on your signal generator and it starts to set up a wave in a solid, which is the string. And you play around with the settings, and eventually you get to a point where it kind of looks like this. Okay, so the string will swap between being in the solid line and being in the dotted line. It's called a standing wave. It's kind of cool because these points here that I'm just highlighting in green, those won't change. The string itself will swap between those two forms, but overall it won't change. Now, how do you go about working this out? Because what you need is you need frequency and you need the wavelength. Okay, so how do you go about working out the wavelength? Well, the wavelength is the distance of one wave to complete, which if we start here, it goes up and down and back up, it would be here. That distance there, if I get my ruler, is one wavelength. Okay, one wavelength. The problem is though, that's going to be a right pain in the neck trying to measure it while the string is twitching around all over the place. So you'll probably end up measuring it from the bridge back to where the string joins onto the machine. And that is going to be an additional 0.5 wavelengths. Yeah, half a wave. How do we go about unpicking that then? Well, let's say, for example, that the length of 1.5 wavelengths, 1.5 wavelengths, was 1.5 meters. How do we go about working out what one wavelength is? Because what we want is we want one wavelength, this distance here. Well, what we're going to do is we're going to chop up that 1.5 wavelengths, and then we're going to multiply back up. So what we're going to do is we're going to work out what half a wavelength is, and then we can times it up by 2. So we're going to divide that by 2 and divide that by 3, divide that by 3 because we're going to chop it up into 3 bits, 3 halves. And we're going to divide that by 3 as well. So that means that 0.5 wavelengths will equal 0.5 meters. We can then times it up by 2 to work out what one wavelength is. and it comes out as being 1 meter. See, you might have to play around with it ever so slightly to work out what the length of one wavelength is. The exact number of wavelengths or multiples of wavelengths that you'll be dealing with depends on how much string you're using and what setting you've got your vibration generator on. If you want to know frequency, because remember, frequency was something that we needed as well. We needed to have the frequency. If you want the frequency, just look at the machine. Because you will have turned the frequency dial to a setting on there and it will tell you what the frequency is. So we'll plug that into our equation. So wave speed equals frequency times wavelength. So let's say, for the sake of argument, that my frequency that I turned the machine to was 10 Hertz. So let's say that it's 10 Hertz multiplied by the wavelength, which I worked out earlier was 1 meter. Because if 1.5 wavelengths is 1.5 meters, then one wavelength must be 1 meter. Equals 10 meters per second. Okay, those are just some example numbers that I've thrown in just so we can practice using the equation. So that was waves in a solid. Let's talk about waves in a liquid then. Let's talk about the ripple tank. So I pinched this lovely diagram off Wikicommons. Thanks, guys. So this is a ripple tank. The one you will use or have used will be something very much like this. So what you've got is you have got a tank. And basically it's a box with a transparent bottom, and it is filled up with water to a shallow depth, hence shallow tank of water. There will be a light source of some kind. Here it's a bulb. You'll probably use a lamp or something like that, and it will shine through the ripple tank and cast, or will cast, some shadows on the table underneath. Over here, this oscillating paddle thing is basically a bit of wood with a motor on the top, and it is going to bounce up and down, and it is going to create ripples in the water. And the power supply over here is something that's going to provide current to make the motor bounce up and down. So you switch it on, the motor starts bouncing the paddle up and down, and it creates a wave pattern like this on the bottom. So we need wavelength and we need frequency. So what you might need to do at this point is to use, I don't know, some sort of handheld device with a camera on, none spring to mind, to take a still picture of your ripple pattern, like so. What you then might need to do is then get your ruler and measure the distance of one wave. So I've got the start of one wave here, the crest of one wave there, I guess, would be a better way of saying it. And again there, and then you would need to go and measure the distance between those two. If that seemed like it was going to be inaccurate because these waves can sometimes be a bit broad, again, what you could do is take it from there to, let's say, there. So we're going to kind of get a bit of an average. And I could measure that distance there. And I know that that distance is 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, 5 wavelengths, 6 wavelengths. So let's say that I've measured it accurately, and let's say that the wavelength there is 10 centimeters. How do I go about assessing frequency? Well, what you can do is you can get something, like a bit of paper or something, and put it underneath the wave tank, so the ripple tank, like so, and maybe you can do something like draw a line on it, like that. And then what you can do is you can count how many waves go past that point in 1 second. That is, after all, what frequency is. Because remember, frequency is waves passing a point every second. Now, depending on the exact setting of your paddle and how much it's vibrating, that might be too fast. You might struggle to see that. And if only there was some way to access some electronic device that had a camera, video, and was able to video things and was perhaps able to play things back slowly. I don't know where anyone would get such a thing. So you could say, you could count on the timestamp on a video from such a hypothetical device, and you might find out that maybe 10 waves were going past per second, which means it would have a frequency of 10 hertz. What if it was slower than that? What if you looked at your hypothetical video and you found out that only, I don't know, 5 waves went past in 10 seconds? Well, you could divide the 5 by the 10, the waves by the seconds. So 5 divided by 10 would be 0.5. So in this case, the frequency would be 0.5 hertz. Okay, so let's plug some numbers into the wave speed equation, have a bit of a play with that. Wave speed equals frequency times by wavelength. So the frequency, let's pick that frequency there, 0.5 hertz, 0.5 hertz multiplied by the wavelength. Now the wavelength is 10 centimeters, that's no good because I need it in meters, so that will be 10 divided by 100, 0.1, so that's 0.1 meters. And if those two values were true, it would be 0.5 times by 0.1, 0.05 meters per second. Brilliant. Thank you very much.